Hi to the CS staff, all my classmates, and anyone watching my recording. I'm excited to present to you my independent work titled Predicting NBA Salaries Through Regression. My advisor was Dr. Xiaoyan Li. My name is Mahmoudal, and I was a student in IWO2. Let's get started. So to motivate my project, I want to explain the concept of the salary cap in the National Basketball Association, or the NBA. So the salary cap in the NBA serves as a spending limit, restricting how much a team can spend on salaries in a given season. So you can almost think of this as a team budget. However, some teams will frequently overspend and go above this. So the NBA disincentivizes this through a luxury tax. So teams who spend over that salary cap have to pay an extra price. So this really does make teams have to consider all the different aspects of a player before deciding how much to spend on a contract. So a big reason why I want to explore this topic is there's very little public discussion about the decision making that goes into these contracts, and I was really curious about how exactly teams sort of go about creating these contracts and deciding what values to put. So the research question that I ask is, can we predict a reasonable salary for a player based on their performance? And I opted for regression methods to help solve this problem. So first, I want to discuss some related works. So a paper from Wu uses NBA data to predict the salaries, but they use regression. They use a classification with k-nearest neighbors, which groups players with similar features and assigns salary ranges for those players. Other related works includes a paper from Papadaki, which actually uses 3 seasons of NBA data to predict salaries. However, they only use a lasso regression, and they were able to achieve an R-squared value of around 0.61. And lastly, a paper from Loth uses regression techniques, but for general salary predictions, some more typical features such as experience, education, and college major. So my goal is to use, of course, a lot of these just same sort of factors that were used in these papers, but more tailored towards a regression-based approach that predicts a specific salary number and also hoping to achieve a greater R-squared value than 0.61. So I use a typical framework for regression, which involves data scraping, storing the data, cleaning and processing that data, training and test split, applying different regression methods, followed by hyperparameter tuning, and then evaluation. So I use Google Colab in order to run my Python notebooks because Colab is suited for computationally expensive operations, which include web requests, storing in large pandas data frames, graphing all the data, etc. So let's actually take a look at the raw data set. So the main data sources that I had to use were NBA player statistics scraped from basketball references, which I used through an API. I also scraped the salary cap information from another website, and also the player salaries from hoopshype.com. So these were all the websites that I used to scrape my data. So one of the things to first notice when we actually get the salary cap is the salary cap goes up year by year. So this is actually very important to consider because this means that we can't just predict a person's salary just using the features. We really do care about the salary cap for that given season as it determines how much the team is willing to spend. So one of the decisions that I make is to normalize player salaries across the different seasons. So therefore, instead of predicting an exact amount that a player should be making, we'll predict a percentage of the salary cap, which can then be multiplied by that given season salary cap to determine what's a reasonable price a team would be willing to spend on a player. So after actually merging all the data sets together, the main target variable, as I mentioned, is we need to create the percentage of the salary cap features, which is calculated as the player's salary for that season divided by the salary cap of that season. So the final data set, just from merging everything, came out to around 2,071 rows and with 80 features. And of course, we want to restrict the number of features, and I had to figure out ways using feature engineering techniques to further reduce my feature size. So my approach was to use a correlation heat map, which helps me narrow down features that most directly correlate with the target variable. And if we actually look at some of these features, which the correlation map gave me, they intuitively make sense as to what features teams may be prioritizing when signing a player, like field goals, which is the number of baskets a player lands, and how many points they earn for the team. I then plotted the data plots to see what the scatter plots look like. And one thing to notice is some of these variables are highly redundant to each other. For example, field goals and field goals attempted. So I also needed to consider that and filter out redundant features so I don't have any redundancy in the feature set that I'm choosing. So I did have to filter some of the features out as well. So upon running a baseline regression model, we can see that we achieve an RMSE of around 5.1%, and our R squared is around 0.615. So doing very similar to the Papadaki paper that I mentioned. And I sort of wanted to see how can I further improve the R squared values, and I decided to look at the residual plot. So we can see that the module does have some large discrepancy. It does heavily underestimate and overestimate some players. So I decided to further just look into what types of players the model is underpredicting. So upon printing out these players, one of the things I noticed is that players with a large branding are typically underestimated by my model, which makes sense intuitively because teams are willing to spend more money on players with larger branding because brand deals are also a thing that teams consider when they're signing up players. So this brought up a new question: what other features should I consider in order to capture a player's branding? So this is where I decided to look into Instagram following, as players with a higher Instagram following typically mean that they have a bigger brand and are very popular. So once I incorporated the Instagram following and also applied hyperparameter tuning, I then saw a massive performance gain in terms of the nonlinear regression methods, where I was able to spike up the R squared value up to 0.66. So this was definitely a worthwhile sort of feature to include, as the nonlinear regression, specifically gradient boost and random forest models, perform way better than the linear methods, the linear lasso, ridge, and elastic net, which didn't see much of a performance gain. So to conclude, we achieved a best R squared value of 0.66, which indicates that our input feature set is definitely a good predictor for our target variable, which is the percentage of the salary cap. And as we saw, the nonlinear regression models perform better than the linear regression models. If we actually see the most important features for the random forest model, we can actually see that the Instagram following contributed to 9.6% of the target variable, which was definitely substantial. One of the reasons why the linear regression models may have not performed as good is because we can actually see that there's very low correlation between the percentage of salary cap versus the Instagram following. So it's more likely for a nonlinear regression model to see the fact that players with very high Instagram followings are more likely to get a bigger salary amount. So as we can see, the outliers for this graph or for this plot, typically players with very high Instagram followings lean towards more the side of higher salary caps. Now, to discuss some of the limitations, as I mentioned, there's very little public discussions on how NBA teams decide player salaries. So a lot of my features are definitely speculation and reasoning about some of the features that NBA teams might prioritize over others. Another limitation is that Instagram following is just one of several options for a player's personal brand. There are other social handles that may be correlated with a person's branding, such as a Twitter following, for example, or other sort of social handles. Another limitation was that the time series data for Instagram wasn't available, so I was only looking at the present Instagram following. So that might not be accurate, considering that we are using data from 4 seasons ago, where a person's branding or Instagram following may not have been as high. And finally, the current model ignores players based on their free agency. So free agency refers to whether a player has been signed onto a team for multiple seasons, or they're no longer signed to a team, so are now free to explore other options. So this is relevant because some contracts are typically multi-year, where a player gets a specified amount, a similar amount across all the years. So the model doesn't take into consideration that. So the model would definitely be more tailored towards players who are on free agency, and where teams would definitely want to give a player a brand new contract. With that, I want to say a huge thank you to my advisor, Dr. Xiaoyan Li, my TA, Lauren Okamoto, as well as all my IW classmates for helping me along with this project.